let's have a look at how we can graph a basic exponential function. Now, an exponential function is of this form: y equals something to the power of x. And it takes this shape, it comes along and then goes up very, very sharply for some reasons that we'll explore in a moment. Now, there's one thing that we can say about a: it can't be 1. Now, let's consider why not. If a was 1, then if we sub in various other values of x, 1 to the power of anything is still just 1. So that then it wouldn't have this characteristic shape that exponential functions have. So a can be anything other than 1. Now, looking at the domain and the range, the domain is all real x. And the reason for that is that we can take any number and sub it in here for x, and we can raise any number to any other number. So that's all quite possible. These two numbers can be anything at all. So it makes sense that the graph exists as far towards infinity and negative infinity as we like on the x-axis. But when we look at the range, we see something happens here. Y has to be greater than 0, and in fact it can't actually even equal 0. Now, if y can't equal 0, we basically put a dotted line all the way along the line y equals 0, which is actually the x-axis, to say the graph can't go here, okay? And that is called an asymptote. So we show it with a dotted line, and that's something that is a real feature of this graph. Now, why can't y equal 0? And in fact, why can't y be negative? Well, let's sub some values in and just think about what happens. And making a table of values is always a good way to know how to graph something if you're not sure of the shape. Now, I'd be tempted just to start by looking from here to here. I've graphed -2, -1, 0, 1, and 2. Well, I haven't graphed them, I've put them into my table of values. And if I consider what happens when I sub in x equals -2 here, and we look at a graph like, well, let's let a equal 2 to start with. Then if I was raising 2 to a bunch of different numbers, 2 to the power of -2, that's the same as 1 over 2 squared. And that's a quarter, so I've put that in here. If I raise 2 to the power of -1, now I've got a half, because it's just 1 over 2 to the power of 1. So I've got that here. If I raise 2 to the power of 0, I get 1. So that's my answer here. And now if I raise 2 to increasingly bigger and bigger numbers, 2 to the power of 1 is 2, 2 to the power of 2 is 4. I've put a really big number in here just to ask myself, what happens when x is 100? Well, I'm going to have 2 to the power of 100, which I'm going to tell you a story in class tomorrow, which will hopefully make you understand that this number is mind-bogglingly big. It's so big that our tiny brains can't really even properly comprehend just how large it really is. Now, at the other end of the scale, if we just go into the negative numbers, not that far, but let's just go down to something like -100. If we raise 2 to the power of -100, we know from our work with negative indices in Year 10 that that means 1 over 2 to the power of 100. Now, I've just warned you that this number on the denominator here is huge. So 1 over a really huge number is a tiny, tiny, tiny fraction, isn't it? It's very, very, very close to 0. But no matter how far we go to the left here and put in, much, much larger negative numbers, we're never going to get 0 because we're always going to get 1 over an increasingly large number on the bottom. So our fraction gets tinier and tinier and tinier the further we go to the left. The further we go to the right, we get into astronomically huge numbers really quite quickly. Even when x is only 100, which is really not that big of a number, the y value is massive. So if you thought that a parabola went up sharply, let's compare one of these to a parabola, just for argument's sake. Then if we had a formula like y equals x squared, when x is 100 there, we've got 100 squared. Pretty big number, 10,000. But when we have y equals 2 to the power of x, and we let x equal 100, 2 to the power of 100 is many, many, many times more massive. So that explains why this graph comes along and it goes up very, very sharply here. Now, something else that we always need to show on these graphs, we always show the asymptote. It goes along the x-axis. We always show any intercepts that there are. Now, you'll notice there's a y-intercept here at 1. Well, there's always a y-intercept at 1, no matter what value you have here for a. And that's because anything to the power of 0 is 1. You might want to write that down in your notes if that's not something that's easy and obvious for you to understand. Anything to the power of 0 is 1. And so no matter what a is, we are always going to have a y-intercept of 1 for all the values of a. So you can always put that in first, draw your asymptote, and then just draw a line that goes sweeping up sharply. Now, depending on what this A value is going to stretch our curve and make it sort of stretched out one way or the other. So to give your graph some scale, there's a convention of always putting at least one other point on your graph. So you don't need a whole table of values. Once you know the basic shape of one of these, you can put your asymptote, you can put your y-intercept at 1, and then you can just get the general shape of the curve right. But always put another point in. Something like, let's let x be 1, what would y be? So subbing in, if we've got this graph, y equals 2 to the power of x. If x is 1, y is 2, and so I've included the point 1, 2, just to give my graph a little bit of scale. And thinking about how the numbers would change, if I was to graph y equals 3 to the power of x on the same axis here, it's going to have the same y-intercept, but when x equals 1, y would equal 3 to the power of 1, which would be 3. So that would put it up higher, wouldn't it? It'd be up here somewhere. And so you can see, I think, that as this number gets bigger, your graph is going to rise up ever more sharply and steeply. And down on the other side here, it's going to come down actually even closer to the x-axis than for lower values of a. Now we should also have a quick look at exponential functions where the power is negative x. Now if we replace this generic a here just with something nice and simple like a 2 so that we can graph it, then we can see that what actually happens here is that we get a reflection around the y-axis of our other basic exponential function, y equals 2 to the power of x. So instead of going up like this, our new curve goes the other way around. It still has an asymptote, which we draw as a dotted line along the x-axis, and it still cuts through the y-axis at 1. Now let's consider why all of this happens. If we just consider various values for x, let's say when x equals 0, we've still got 2 to the power of 0, because negative 0 is still 0, right? So we still get y equals 1 when x is 0. When x equals 1 though, now we have 2 to the power of negative 1, and that's a half. So when x equals 1, y equals half, we could put that in as our extra 1 point because we know we have to label at least 1 point. So letting x equal 1 and finding out what y is makes some sense. And then as we go up and sub in increasingly higher values for x here, for example, x equals 2, we're going to have 2 to the power of negative 2, and that gives us a quarter, and then we'll have an eighth, etc., etc. So as we go along, we're going to get closer and closer to that x-axis, but never actually meet it. And as we go this way, if we sub in x being, say, negative 1, we've got negative 1, which is just 1. So over here we'd have the point negative 1, 2. And just as our other graph went sharply up on the right-hand side, this one's going to do the exact same on the opposite side of the y-axis.